Welcome to Ghumman Tech, your go-to destination for all things aviation and technology. In this comprehensive tutorial, we'll delve into the intricate world of the Cessna 172's dashboard indicators. Whether you're a seasoned pilot looking to brush up on your knowledge, or an aspiring aviator eager to understand the ins and outs of cockpit instrumentation, you've come to the right place. Join us as we dissect each indicator, unravel its significance, and equip you with the essential know-how to navigate the skies with confidence. So buckle up and let's soar into the fascinating realm of aviation instrumentation. The airspeed indicator displays the aircraft's speed through the air, measured in knots or miles per hour. Pilots rely on the airspeed indicator to maintain safe flying speeds during various phases of flight, including takeoff, landing, and cruising. For example, during takeoff, the pilot uses the airspeed indicator to ensure the aircraft reaches a minimum safe flying speed before lifting off the runway. Maintaining proper airspeed is crucial for aircraft stability and control. Flying too slow can result in a stall, while flying too fast can lead to structural damage. An interesting fact about the airspeed indicator is that it measures indicated airspeed, IAS, which may differ from true airspeed, TAS, due to factors such as altitude and air density. The altimeter indicates the aircraft's altitude above sea level. Pilots use the altimeter to navigate safely and comply with altitude restrictions, especially during instrument flight. When approaching an airport, the altimeter helps the pilot maintain the correct altitude for a safe descent and landing. Accurate altitude information is crucial for terrain clearance, obstacle avoidance, and maintaining safe separation from other aircraft. An interesting fact about the altimeter is that it operates based on atmospheric pressure changes, with standard atmospheric pressure at sea level being 29.92 inches of mercury, in Hg, or 1013.2 millibars, MB. The vertical speed indicator shows the rate of climb or descent in feet per minute. Pilots use the VSI to control the aircraft's vertical speed during ascent, descent, and level flight. For example, when leveling off at a cruising altitude, the VSI helps the pilot adjust the aircraft's pitch to maintain a steady altitude. Monitoring vertical speed helps pilots maintain altitude control, especially during instrument flight and in congested airspace. An interesting fact about the VSI is that it operates based on changes in static air pressure, using a diaphragm connected to an aneroid capsule. The attitude indicator, also known as the artificial horizon, provides information on the aircraft's pitch and roll attitude relative to the horizon. Pilots rely on the attitude indicator for maintaining aircraft attitude, especially in low visibility conditions or when flying solely by reference to instruments. During instrument flight, the attitude indicator helps the pilot maintain a level attitude despite visual cues being obscured. The attitude indicator is crucial for spatial orientation and preventing spatial disorientation, a leading cause of accidents in aviation. An interesting fact about the attitude indicator is that it uses gyroscopes to maintain stability and provide accurate pitch and roll information, making it one of the most reliable instruments in the cockpit. The turn coordinator indicates the rate of turn and coordination of turns using a miniature aircraft symbol and a ball. Pilots use the turn coordinator to execute coordinated turns and maintain aircraft control during maneuvering. When making a turn, the turn coordinator helps the pilot coordinate aileron and rudder inputs to maintain balanced flight. Coordinated turns are essential for preventing slips and skids, minimizing drag, and maintaining stability during flight. An interesting fact about the turn coordinator is that it combines aspects of both a turn indicator and a coordination ball, providing comprehensive information on aircraft turns and coordination. The heading indicator displays the aircraft's heading in degrees. Pilots rely on the heading indicator to maintain the desired direction of flight, especially during navigation and course corrections. For example, during a cross-country flight, the heading indicator helps the pilot maintain the intended course by providing continuous heading reference. Accurate heading information is crucial for navigation, especially when flying to specific waypoints or destinations. An interesting fact about the heading indicator is that it uses a gyroscope to maintain its orientation relative to magnetic north, providing stable heading information even in turbulent conditions. The vertical card compass provides magnetic heading information. Pilots use the vertical card compass to navigate based on magnetic north and determine the aircraft's heading relative to magnetic poles. For example, during visual navigation, the vertical card compass helps the pilot maintain the desired heading when flying in areas with limited or no navigation aids. Magnetic heading information is essential for accurate navigation, especially when flying in areas with magnetic variation. An interesting fact about the vertical card compass is that it uses a magnetized card and a damping system to provide stable heading information despite aircraft maneuvers. The tachometer measures engine RPM, revolutions per minute. Pilots use the tachometer to monitor engine performance and ensure proper operation of the aircraft's engine. For example, during takeoff and climb, the pilot monitors the tachometer to ensure the engine is producing sufficient power for safe flight. Engine RPM information is crucial for maintaining optimal engine performance, fuel efficiency, and preventing engine overspeed or underspeed conditions. An interesting fact about the tachometer is that it measures engine RPM by counting the number of revolutions of the engine's crankshaft per minute. The oil pressure gauge monitors the engine's oil pressure. Pilots rely on the oil pressure gauge to ensure proper lubrication of the engine's moving parts and prevent engine damage due to oil starvation. For example, during engine startup, the pilot monitors the oil pressure gauge to ensure oil pressure builds up to the required level. Adequate oil pressure is crucial for maintaining engine reliability, reducing wear and tear on engine components, and preventing catastrophic engine failure. An interesting fact about the oil pressure gauge is that it measures oil pressure in pounds per square inch, psi, or kilopascals, kPa, depending on the aircraft system. The oil temperature gauge indicates the temperature of the engine's oil. Pilots use the oil temperature gauge to monitor the operating temperature of the engine's oil and ensure it remains within safe operating limits. For example, during climb and cruise, the pilot monitors the oil temperature gauge to ensure the engine's oil does not overheat, which could lead to oil degradation or engine damage. Proper oil temperature is crucial for maintaining engine efficiency, preventing oil breakdown, and ensuring engine longevity. An interesting fact about the oil temperature gauge is that it measures oil temperature in degrees Fahrenheit or Celsius, depending on the aircraft's system. The fuel quantity gauges display the amount of fuel in the aircraft's fuel tanks. Pilots rely on fuel quantity gauges to monitor fuel levels and ensure they have sufficient fuel for the planned flight. For example, during pre-flight checks, the pilot verifies fuel quantity to determine if additional fueling is necessary for the intended journey. Accurate fuel quantity information is crucial for flight planning, fuel management, and preventing fuel exhaustion. An interesting fact about fuel quantity gauges is that they may use different technologies, such as capacitance, float-type sensors, or electronic sensors, to measure fuel levels accurately. The manifold pressure gauge shows the pressure of the air-fuel mixture in the engine's intake manifold. Pilots use the manifold pressure gauge to adjust engine power and optimize performance during different flight conditions. For example, during climb, the pilot adjusts manifold pressure to maintain the desired climb rate while avoiding engine stress. Monitoring manifold pressure helps pilots manage engine power, fuel consumption, and engine performance. An interesting fact about the manifold pressure gauge is that it measures pressure in inches of mercury, (inHg), or pounds per square inch, (psi), depending on the aircraft's engine system. The cylinder head temperature, CHT gauge, monitors the temperature of the engine cylinders. Pilots rely on the CHT gauge to ensure the engine operates within safe temperature limits and prevent overheating or engine damage. For example, during climb, the pilot monitors CHT to prevent cylinder temperatures from exceeding maximum allowable limits. Proper cylinder head temperature management is crucial for engine reliability, performance, and longevity. An interesting fact about the CHT gauge is that it helps pilots detect engine anomalies, such as cooling system malfunctions or cylinder leaks, by monitoring temperature trends during flight. The carburetor temperature gauge measures the temperature of the carburetor. Pilots use the carburetor temperature gauge to monitor carburetor heat and prevent carburetor icing, especially during cold weather operations. For example, during descent, the pilot adjusts carburetor heat to prevent ice formation in the carburetor throat, which could disrupt engine operation. Monitoring carburetor temperature helps pilots maintain engine performance, prevent icing-related engine failures, and ensure safe operation in icing conditions. An interesting fact about the carburetor temperature gauge is that it measures temperature in degrees Fahrenheit or Celsius, depending on the aircraft system. The ammeter voltmeter indicates the electrical system's status and charge. Pilots use the ammeter voltmeter to monitor the aircraft's electrical system and ensure proper functioning of electrical components. For example, during flight, the pilot monitors the ammeter voltmeter to detect abnormal electrical loads or charging system malfunctions. Monitoring electrical system status helps pilots prevent electrical failures, ensure system reliability, and maintain electrical system integrity. An interesting fact about the ammeter voltmeter is that it provides real-time information on the electrical system's performance, including battery charge-discharge rates and alternator generator output. The flap position indicator shows the position of the flaps, extended or retracted. Pilots rely on the flap position indicator to monitor the status of the flaps and ensure proper configuration during takeoff, landing, and maneuvering. For example, during landing, the pilot uses the flap position indicator to verify that the flaps are fully extended for maximum lift and drag reduction. Monitoring flap position helps pilots optimize aircraft performance, improve maneuverability, and ensure safe operation during critical phases of flight. An interesting fact about the flap position indicator is that it may be integrated into the aircraft's cockpit display or indicated by a series of lights or markings on the instrument panel. The landing gear position indicator indicates whether the landing gear is up or down. Pilots use the landing gear position indicator to verify the status of the landing gear and ensure safe gear operation during takeoff, landing, and emergency procedures. For example, during approach and landing, the pilot checks the landing gear position indicator to confirm that the landing gear is down and locked for landing. Monitoring landing gear position helps pilots prevent gear-related accidents, ensure proper gear deployment, and maintain safe ground operations. An interesting fact about the landing gear position indicator is that it may include visual, auditory, or electronic cues to alert pilots of gear status changes or abnormalities. The stall warning indicator alerts the pilot of an impending stall. Pilots rely on the stall warning indicator to detect aerodynamic stall conditions and take corrective action to prevent a stall. For example, during slow flight or high angle of attack maneuvers, the stall warning indicator provides an audible or visual warning to alert the pilot of approaching stall conditions. Stall warning indicators are critical for flight safety, providing pilots with timely information to prevent loss of control and maintain aircraft stability. An interesting fact about the stall warning indicator is that it may use various sensors, such as angle of attack vanes, stall strips, or pressure sensors, to detect airflow separation and impending stall conditions. The fuel pressure gauge monitors the pressure of fuel in the aircraft's fuel system. Pilots use the fuel pressure gauge to ensure proper fuel flow and prevent fuel starvation or engine failure due to fuel system malfunctions. For example, during flight, the pilot monitors the fuel pressure gauge to verify that fuel pressure remains within acceptable limits, indicating proper fuel system operation. Monitoring fuel pressure helps pilots detect fuel system anomalies, prevent engine damage, and ensure continuous fuel supply to the engine. An interesting fact about the fuel pressure gauge is that it may use mechanical, electrical, or digital sensors to measure fuel pressure and provide real-time feedback to the pilot. The outside air temperature, OAT gauge, displays the temperature outside the aircraft. Pilots use the OAT gauge to monitor ambient temperature and assess atmospheric conditions during flight. For example, during climb, the pilot monitors the OAT gauge to determine temperature changes and anticipate icing or turbulence conditions. Monitoring outside air temperature helps pilots make informed decisions regarding aircraft performance, fuel consumption, and weather avoidance. An interesting fact about the OAT gauge is that it may provide valuable information for calculating true airspeed, density altitude, and aircraft performance adjustments based on temperature variations. Thank you for joining us on this journey through the fascinating world of aviation instrumentation. If you found this video informative and engaging, don't forget to subscribe to our channel for more insightful content on aviation and technology. Help us grow our community by sharing this video with your friends, fellow aviation enthusiasts, and anyone interested in mastering the Cessna 172 dashboard indicators. And remember to hit the like button if you enjoyed what you saw. Together, let's continue exploring the skies with Ghumman Tech. Safe flying, and see you in the next video.